Chapter 2. In Chapter 2, we're going to be talking about linear functions and equations. Section 2.1, we're going to talk about linear functions as models. Models are used in math, chemistry, physics, and even religion. A model looks like this. Future equals present plus change. Every model must be able to predict something. Okay. And then we have some present value plus whatever change. Models are used to predict weather, epidemics, business trends, and many other things in our everyday lives. Representations of a linear function should look familiar. F of x equals mx plus b. Remember, m is our slope and b is our y-intercept, so some point 0, comma b. A definition, a zero of a function is the x-intercept. Remember, y-intercept crosses y-axis, x-intercept crosses the x-axis. Okay. So a zero of a function is another way to say x-intercept. Linear functions are either always increasing or always decreasing. Okay. For example, the slope of this line, okay? Remember, slope is change in y over change in x. So we, going from this point to this point, we are going up 2, and then we are going to the right 2. So our slope is 1. This is positive, so it's always increasing. The y-intercept, we cross the y-intercept, the y-axis at -2. Our x-intercept, we cross the x-axis at 2. So we can write this as 2, comma 0. We can write this as 0, comma -2. The formula for this would be f of x equals our slope, which was 1, times x, plus our y-intercept, which in this case was -2, which we can write as x minus 2. If I ask you for the zeros, zeros is another word for x-intercept, and in this case, 2 comma 0 or 2 would be our 0. Another way to find the slope, if you don't like to count, okay, you can also use the slope equation where this is 2 comma 0 and this is 0 comma negative 2, and you can plug it into the slope formula that we learned in chapter 1. Models with linear functions. A word problem that can be represented by a linear function is going to look something like this. F of x equals constant rate of change which we learned means slope, times x plus the initial amount. So, for example, a car is traveling at 20 miles per hour and then accelerates at 5 miles per hour each second for 6 seconds. We want to know what the formula is, and we want to know the domain. So our formula is going to be f of x equals, okay, it's easier, I think, to look at the initial amount first. So what is the initial amount here? Initially, the car is traveling at 20 miles per hour, so we're going to have plus 20. Okay. And then our constant rate of change, accelerating, means we're going faster at 5 miles. So 5 is going to be our constant rate of change times x. So our equation is f of x equals 5x plus 20. Our domain, it's traveling for 6 seconds, so we're starting at 0, bracket, and we're going for 6 seconds, bracket. Again, initial amount, traveling 20 miles per hour, accelerating by 5 miles per hour, so 5x plus 20. If we were slowing down, our formula would only change slightly. Our initial amount is still 20, but if we're slowing down 5 miles per hour, it's going to be negative 5x. Another example, a 400-gallon tank is draining at 20 gallons per minute. We want to know the formula for this. F of x is going to equal, again, starting with the initial amount, we have a 400-gallon tank, and then it's draining, so it's becoming less, so it's going to be negative 20x plus 400, because we were draining. If we were filling up, then it would be positive 20. If we want to know after 4 minutes, oops. Okay. x would equal 4. So f of 4 would equal negative 20 times 4 plus 400. So there would be 400 minus 80, 320 gallons left. If we wanted to know the x and y intercept, okay. If we wanted to sketch a graph, okay. At time 0, we had 400 gallons. And then if we were draining 20 gallons per minute, 20 goes into 400, 20 times. Okay. So at time 20, we would have no water left. So our equation and our line would look like this. So in that case, our x-intercept would be 20, 0. And our y-intercept would be 0, 400. If we wanted to know the domain, okay. Our time starts at 0, and after 20 minutes, our tank is completely empty. If you didn't want to sketch a graph, you could also find x and y intercepts like we learned in chapter 1, plugging in 0, for y-intercept, plugging 0 in for x, and for x-intercept, setting it equal to 0. See chapter 1 if you forget how to solve for that. Okay. Now, because models are not perfect, and it's based off of data, okay, sometimes the slope is not always excuse me, the slope is not always the same between all points. But it may be very close. We talked before in chapter 1 that the slope is not constant, then we usually use a non-linear function. However, in real life, if the slopes are pretty close, okay, people might want to still use linear functions as models, okay? So we may still use an approximate linear function. If this is the case, you use the first and last data point to find slope. Okay. Remember using the y2 minus y1 over x2 minus x1, your first and last data points. So for example, I'm going to go to the next page. For example, if we're talking carbon dioxide emissions from planes, where X is our miles, Y is our pounds, we got 240, 360, 680, 800. And then our Y value is 150, 230, 435, and 510. Slopes are not the same throughout, but they are close enough. So we would use 240, 150 and 800, 510 to find the slope. So we would do 510 minus 150 over 800 minus 240, and we would get 360 over 800 minus 240. And then we simplify this to 9 over 14. If they want to know the formula, we know that f of x equals our slope, which we already calculated. And then our y-intercept, they don't give us our y-intercept, but 0, 0 would be our y-intercept, because if we're not traveling any miles, 0 miles, then our carbon dioxide emissions will be 0 pounds. So it would be plus 0, which we wouldn't have to write. Nine divided by 14 as a decimal. If we had f of x equals 0.64x, that would be acceptable as well for word problems. So again, f of x equals 0.64x. If they wanted you to interpret the slope, which we've done before, okay, then we would say we are burning 0.64 pounds of carbon dioxide per mile. Okay. Remember, vertical axis is our pounds, per our x-axis mile. And then if they wanted to know f of 1,000, we would just plug in 0.64 times 1,000, and we would get 640. And if they want to know what does that mean, that means if we travel 1,000 miles, we have a carbon dioxide emission of 640 pounds. So just being able to look at an application, come up with the formula or the model or the function, being able to plug in values, telling people what the slope means, telling people what your answers mean, really important for linear function models. Other linear models, something called a piecewise function. A piecewise function is when pieces of the domain have different equations defined in the function. Another vocabulary word, something is continuous. That means that you can essentially draw a graph without picking up a pencil. Versus discontinuous, discontinuous means the graph has breaks or gaps or jumps. So in other words, discontinuous if you have to lift up your pencil at any time to complete the graph. An example of a piecewise function, f of x equals 1 minus x if -3 is less than or equal to x is less than 0, and 1/2 x if 0 is less than or equal to x is less than or equal to 3. So to draw a piecewise function, okay, I'm going to call this equation 1 and equation 2. So first step, we're going to find endpoints for 1. Okay. So we have 1 minus 3, or excuse me, 1 minus x. Okay, 1 minus x, and we have -3 and 0 as our cutoff values. Okay, -3 and 0. So I'm going to plug each of those in. So -3 will give me 1 minus a -3, which will give me 4. And when I plug in 0, 1 minus 0 gives me 1. Less than, okay, or equal to. That equal to means that it's going to be a closed circle. A less than symbol without means that it's going to be an open circle, because that 0 doesn't technically exist there. So right now we have -3 comma 4 is a closed point, 0 comma 1 is an open point. Second step, we're going to plot those. So we have -3, 4, 1, 2, 3, 1, 2, 3, 4, and it's closed. And then 0, 1 means that we're not going anywhere and we're going up 1. And this is open. Our x value is between the two, so we're just going to draw a line between the two. The third step, we're going to find endpoints for equation 2. So equation 2 was f of x equals 1/2 x. Excuse me. And our endpoints were 0 less than or equal to x less than or equal to 3. So we're going to plug in 0. F of 0 gives us 1/2 times 0, which gives us 0. And then 3. 1/2 times 3 is going to give us 3/2, which is 1.5. This means that the 0, 0 is going to be closed. This means that 3, 1.5 is also closed. Fourth step, we're going to plot those. So I'll go back to the graph we already have. And my 0, 0 was a closed point. And then my 3, 1.5, somewhere here, also closed. X is between them. So we just draw a line between them. Okay. Should look more straight. Okay. And then if they wanted to know continuous or discontinuous, If we start here with our pencil, we're traveling, but then to get to the next part, we have to lift up our pencil, so it would be discontinuous. Same function, I'm just going to rewrite it. 1 minus x for negative 3 less than or equal to x less than or 0. 1/2 x for 0 less than or equal to x less than or equal to 3. If they wanted to know the domain, we know that the domain is all our x values. So we go from negative 3 all the way to 3. That is how we know that they are brackets. If they want to know what f of negative 2 is, we have to figure out where negative 2 is. Is negative 2 between negative 3 and 0, or 0 and 3? Negative 2 is here. So we're plugging it into 1 minus x. 1 minus negative 2 is 3. I asked for f of 0. 0 is here and here, but it's not included here, but it is included here, so we would use this equation. 1/2 times 0 equals 0. If I asked you for f of 2, is 2 between negative 3 and 0? No. Is it between 0 and 3? Yes, so we're using this equation. 1/2 times 2 equals 1. Another example for graphing, x minus 1 for negative 4 less than or equal to x less than 2. Negative 2x for 2 is less than or equal to x less than or equal to 4. First step, okay, endpoints for equation 1. So f of x equals x minus 1. Negative 4 will give us negative 5. Less than or equal to will give us a closed. 2 will give us 1. And this is not equal to, so it'll be open. Second step, we plot it. Negative 4, negative 5. 2, 1. And then x is anywhere between the two. Then next step, we're going to find the endpoints for negative 2x. So just a reminder, 2 less than or equal to x less than or equal to 4. So f of 2 will give us negative 4. This shows us that it will be a closed circle. F of 4 will give us negative 8. That right there, less than or equal to, shows us that it's closed. So if we go back to the graph, 2, negative 4 will be here. Negative 4, oh, that should be positive, excuse me. Positive 4, 1, 2, 3, 4. Negative 8 be down there, close, and x is between the two. This is also discontinuous. Our domain we start all the way over here at -4. And even though we go to 2 here and it doesn't exist there, it does exist down there. So we can keep going to +4. Again, that's our domain. Then we have something called a greatest integer function. F of x equals, then it's a bracket with an extra line, x, bracket with an extra line. And this just means that it's the greatest integer less than or equal to x. It's the greatest integer less than or equal to x. Okay. Remember, integer is all the negatives, 0, and all the positives. So the greatest integer less than or equal to x. So if I gave you this, okay, 3 is an integer, so the answer would be 3. If I gave you 3.2, okay, it's the greatest integer less than, so the greatest integer less than 3.2 would be 3. If I gave you 3.7, okay, even though people would want to round up, because we're using the greatest integer symbol, the greatest integer less than or equal to that would be 3. If we were doing negatives, okay, if I gave you -3, that is an integer, so -3 would be the answer. If I gave you -2.3, negative numbers move in the other direction. So on a number line, we have -2, -2.3, -3. If we're here and we want the integer less than this, -3 is actually smaller. If I gave you -3.1, 3.1, -3.1 is here, so -4 is the integer that is less than or equal. The graph is a glorified piecewise function. So at 1, 1, it exists. So at 1, 1, this exists. And then if we look at 0.5, okay, we would actually have to jump down here because 0.5, the integer that is less than or equal to 0.5 is 0. And then 1.7, so something close to 2, would still be at 1 until we get to 2, and then 2 would jump up to 2. And so it looks like this. This is called a step function because it looks like you're walking up steps. Okay. The graph, not as important to know as how to evaluate the greatest integer function. Okay. Greatest integer function and piecewise functions are used also to represent models, but they're not as common as linear equations. Okay. And that is it for section 2.1.